Okay, so Anata, so we have our CH3. Your butane, no, you have CH3, CH2, CH, CH2 here. So you have, anyway, you have your CH stock. Kita na ninyo, no, which one? The carbon atoms. 1, 2, 3, 1, 2, 3, 4. Okay. The first one is the monobromination. Now you can actually have your bromine on this. Dire, on carbon 1. And you can have on carbon 2. So you have your bromine here. So you have your bromine. And the other one is your, this is the monobromination process. Okay. Of course, you have your Br2 here. It's one of your reagents in the presence of heat or light. So once this, you have your monobromination, you can have your bromination coming apart, no? And you can have your kini. So dibromination, you have your first bromine here, you can have here, but you will notice that for this one, it's actually chiral. Now you have 1, 2, 3. You actually produce this to be chiral. So you can have your hydrogen here, your bromine here to be, this is chiral. Kita bang chiral na siya? You have your hydrogen, and of course you have your bromine, and you have your bromine here, and another one is masayap na ko illustrate. But anyway, you have your two kinds of PR here. Sorry. Dapat baliktad din siya. Dapat ibaylo na nato. Anyway, this carbon here is chiral. So you have this. You can have your second bromination diri on this second, this one first carbon. You can have on second carbon, and you can also have your bromination, your second bromination on 1, 2, 3. Okay, you have that. You have 1, 2, 3, 4 Br. So you start. You have on carbon 1. This is on carbon 1. Carbon 1, this is on carbon 2, right? So this in carbon 2, it's actually chiral. So you actually produce the enantiomers. And then the last one is on carbon 3. You have another bromine. Okay, you have your bromine here. And another one is carbon 3. You can have actually your in carbon 4, no? So napay-daghan nga bromination. Okay, you have your bromine. Let's see how, sorry, bromine here in carbon 3. And if you have bromination in carbon 4, you can also have your bromine here in carbon 4, but you can see on carbon 4, it's actually chiral here. No, chiral ba? So 1, 2, so chiral siya. So you actually get an enantiomer here. Pag-write sa enantiomer, nagtakalimot. Pag-write sa enantiomer. It's the way to write the enantiomer. The enantiomer will be 1, 2, 3, 4 non-BR. You have your actually the hydrogen dapat pag-write na rin is August. You will have your you have your CH, and then of course your hydrogen, hydrogen, and then your BR. Okay, you have your BR here. So this is the mirror image of this one. Okay, what else? So aside, okay, ano to? aside from carbon 1, 2, 3, 4, no, carbon 4 ni. Now you get an enantiomer also for this. And your enantiomer, so on pag-write sa enantiomer, now you have your enantiomer will be so you have your Br here, and you have your H3, and then copy this. You have carbon 1, 2, 3, 4. Okay, so this is the enantiomer of this. And then isa pa, so we have on carbon 4 another bromination process, second bromination process, no? On carbon 4 ni, so you can have on carbon, carbon 1, 2, carbon 2 din ni. Carbon 2, carbon 1. Ani, balik naman ko, ani. Wala na din ni. Sorry. Okay, so the other one, tingog mo ha, o saan na akong gipang din. Br2, of course, another Br2. Klaro ba ang reaction sa ibabaw? You will have your, from carbon 1, 1, 1, 2. This is 2. And this is 3. It's not 4. This is 3 and this is 4. And the other one is on carbon 4. Okay, so we are 1, 2, 3, 4. Okay, so how many products? So you have 1, 2, 3, 4. And so balik ta diri sa atong we will just move this down. Okay, so let's proceed first with the bromination of our, of course, you have your Br2 here. So earlier we have the monobromination on carbon 1. So you have the bromination on carbon 2, and then you can proceed with another bromination. So you can attack this on this. Another Br, of course, in the presence of light, you can have Br and another Br here, right? But this Br here is also, this one actually is chiral, right? This one is chiral, and this one too is chiral. So you can get 4, there are 2 chiral centers here. Sorry. Okay. You have 2 chiral products. You have 2 chiral compounds. Okay. Let's say the first one is kani. Okay, plus the other one is right. You have this, and you have your Br2. Okay, in the presence of light. Balik to sa first. Kung kaning first nga enantiomer of the first product, you can actually have this. But this one also is chiral, right? So you can have this. And plus the enantiomer of this, you will have you have your Br, and then you have this. Okay, and then of course you have kanina pod. So if one is R, the other is S, we don't know. So this is Br, and since you produce a chiral center here, so it can either be Br. We'll start na ng tani. And then you can have BR, and then you have BR. Okay, so in general, your combination, there's two, you can have 2 and 3 men, or you can have 2s and 2s. And then you can have your okay, assign na lang niyo later, but I just want to say that your products, you can have your you can have your 2s, you can have your 2s, 3s. You can have your 2r, 3r. You can have your 2s, 3r, and you can have your 2s, 3s, 2r, 3r, and then you have patong SS, RR, 2R, 3S, right? So there are two chiral cemeteries. You expect to have 4 stereoisomers for that reaction, right? So unsa pa? Can you think of any other product for this? So from here, you get this is a mixture. A mixture, this one are enantiomers. These two are enantiomers. Enantiomers. And the two are canicilla are also enantiomers. The two are enantiomers. So after you get your kani, no? So napakailaing product ana. Asa man ka pwede mag-form. Pwede ka mag-form of this is 2,3 and 2 second carbon and third carbon. Okay, but you can also have 2,2, and you can also have this. The concrete product. You can have this. Okay, so anyway, I think that you were able to follow na, Control Z. You can have your other product will be dali na lang ko masumpay. Baro pa ba akong kain? Masumpay ta here. Another BR2 is kani kung gikan dali, no? What will happen is you can also have your BR nimo, which will be here, your BR. So either way, no, either kani or kana, you actually have your kani nga BR. Where else? Either man day sa duha. Actually get the same. Okay, BR man. Okay, so anyway, either of these two enantiomer you actually get the same. It's not chiral. You will have so either way, no, you actually get the same because this is not a chiral compound. And the next is this is on carbon 2 and 2, 3. So you have your padipodiri, no? So 1, 3, I think. Nabatay 1, 3 sa ibabaw. Kung wala na tayo 1, 3 sa ibabaw. 1, 1, 1, 1, 2, 1, 3. So, pwede na. 1, 3 na ta dili. So, pwede na ta dili mag 1, 3 diri yung dapita. Okay, so that's all our products. Sakto na din itong products. Pwede na ta dili mag 1, 3 diri kay ang carbon 2. This is already carbon 2. It's 1, 3, 2, 3. Kay naanay 1, 3 sa 2, 3, sorry, 2, 4. Kay naanay 1, 3 sa ibabaw. Kani 1, 3. Okay? So how many products? So like 1, 2, 3, 4, 5, 6, 7 ba? Let's look at 1, 2, 3, 4, 5, 6. Na siguro kayo nabalik. No? 1, 2, 3, 4, 5, 6. Okay, so I think nagbalik-balik ko. Here you have, yeah, this one is just 2, 2. 2, 2, 2, 3. So actually, it's a mirror image of the other. So dapat nalubra ko sa akong isa, no? 2, 2 man siya. And then you have, yeah, it's not 5-membered carbon. So, balik ta. Actually, the same already. Because what we get actually is kani 2, 3. We actually get a meso compound. So either way, kani siya. Either way, no, iplahi lang siya because you have CH, you actually get a meso compound here. So you only get 1, 2s and 2ss and 2, 3ss and 2r, 3r. Okay, so wala na ning isa. Kay when we count from left to right, pareha raman. Kani ang sobra. Okay. You have 1, 2, 3, 4, 5, and 6. Seven. 1, 2, 3, 4, 5, 6. Tama ko, 7. B. Naman sa tanay. Two, 3. Tama, you have 1, 2, 3, 4, 5, 6, 7. Tama, 7. So there's too many. You have, tama lagi ko, you have 2 chiral centers because each of these are chiral centers. Okay, do you have questions? Larger gitanin ko. In alkyl, you can have too many products, no? And we only have to limit like here. It's very specific that we only have to do dibrominations. Imagine if we have tripano, we have another mole of our bromine, and imagine another product that could be obtained. Okay, so here is practice 10.10. You can do your activity here. Consider the monochlorination. This is just a monochlorination process. So imagine if you still do further, dichlorination. The only thing when you have when you proceed with the second halogenation is you have to think, or even in the monohalogenation, you have to see whether the product that you will obtain will contain a chiral center, because it will lead to enantiomers, racemic forms, like this one. Like this one, the second carbon, you will first produce your enantiomers and actually have B and B. You can actually obtain another enantiomers, and that the 1, 2, 3, 4, they are actually D-estramers. Okay, so you only have to be careful whenever you have a chiral center that's being produced. Let's do here consider the monochronation, assuming that the product of the mixture is. Okay, so whenever you produce the stereomers, you can always separate that one by fractional distillation or by gas chromatography. For enantiomers, yes, chromatography also, you can do chromatography. For chapter 10.10, you can do that with, for you to practice. So let's go to the next topic. It's all about the allylic substitution and allylic radicals. So what do you mean by allylic radicals? So an atom that is bonded to an atom or group that is bonded to an sp3 hybridized carbon adjacent to an alkene double bond, like here. Now you have an sp2 carbon, and then you have an sp3 carbon. This carbon bonded to an sp2 or a double bond carbon having a double bond. This here is what we call as an allylic group. Okay, here you have a double bond carbon utilizing an sp2, forming a double bond here, pi bond. And here, this carbon here, you have an sp3 carbon adjacent to this. This position and this position are what we call as an allylic position, okay? And the group that is here is what we call as the allylic group. So let's say here, this chlorine here is attached to this carbon here, the chlorine and the bromines, sp2, sp3, carbon double bond, and then you have carbon sp3. This chlorine and bromine here are at allylic position. So they are bonded to carbon, in which carbon is at the allylic position. And you call that one as the allylic groups. Okay, so what's so special about allylic position? Allylic hydrogens are especially reactive in radical substitution reactions. Why is that? We can synthesize allylic halides by substitution of allylic radicals. For example, we have your propene reacts with our halogen. Of course, the conditions is at a high temperature or even under the presence of UV, and a low concentration of our halogen, where the concentration of the halogen is small. Even if you have a very low concentration of your halogen, we actually have a substitution reaction here at the allylic position, not here, okay? And so here we have a substitution reaction at the allylic position with our radicals at high temperature or in the presence of radical initiator and low concentration of our halides halogens. What we actually obtain is a substitution reaction. So yun sa na siya, we earlier here. If you remember in your alkenes, so whenever you have your halogens, this halogens will add to your double bond, right? And you actually have your double bond here. But in the presence of a very high temperature and a low concentration of your X2, and in the presence of a radical initiator, the halogens will actually not add to your double bond, no? they actually add to the allylic position in a substitution reaction. So you have to be careful whenever we have allylic positions, because we might, especially for your alkene, no, having allylic positions, no, we may not be able to do addition reactions of our halogen, but instead we do substitution reactions at allylic substitution. So what is the mechanism behind here? Look at the mechanism here. So remember, when you have your double bond in your alkene, chapter 9 baton, no? In the presence of halogen at a low temperature, even at low temperature, the X2, the halogens will add to your alkene. No, it can be added anti. If you have to do this in the presence of organic solvent, right? And the addition is anti, because you will actually get your halonium ion, which is got it's an electrophilic addition reaction. So once you do your 3-membered ring here, the nucleophile will add to the opposite to the ring, and you have the anti-addition. But again, once you have the presence at high temperature, we have allylic substitution reaction. For the addition, it occurs at a low temperature for the addition reaction, but this occurs at a high temperature or in the presence of a radical initiators. It's very important, it's very important to note on the condition of the reaction system, no, because the product might be different depending on the condition or environment of our reagents reactants. So let's look at an example of the allylic chlorination when propene and chlorine react. So you have your propene, and here you have your carbon, which is at an allylic position here, double bond. So what happened here is we do the substitution reaction. We have the chlorination here. You know, the hydrogen is being replaced with chlorine. It's the same reaction with that of your alkanes, no? With halogens. We actually produce C halogen bond. Here in this case, you just have a double bond adjacent to your sp3 carbon. So the mechanism for allylic substitution is the same as the chain mechanism for the alkane halogenation. So the same as alkane, no? Except that na lang tayo double bond makitaan. So here, since it's the sp3 carbon, it's the sp3 carbon that reacts with halogen, you can imagine that's the same with the alkane reaction with halogen. We actually use or initially produce a radical in the reaction. So first, in the presence of high temperature or an initiator, we actually produce halogen radical, so that. And then we have the propagation step that will produce an allylic radical. So you have your chlorine that will obstruct the hydrogen, no? At the allylic position, what we actually obtain is the HCl. So one electron from this chain initiation step, you actually have a homolytic bond cleavage where you have your HCl, 1 electron from chlorine, 1 electron from hydrogen. So from the carbon and hydrogen bond, 1 electron will go to your carbon here. And the carbon dot, this is an allylic radical. Okay. So you notice, by the way, when you have an arrow for a homolytic bond cleavage or homolytic bond position or bond formation, the arrow that you form, no, dili siya arrow nga katong duha bitaw, double wedge na arrow. What you see is kanang isa lang, because it pertains to, or it indicates only one electron that's being produced. Excuse me. Okay, so again, you produce an allylic radical. So once you produce an allylic radical, no, it will react, another radical to react with our halogen radical to form, again, you see the arrow, one dot, and one arrow here. It means that there will be a homolytic bond formation. So one electron and another electron from chlorine, we actually produce this carbon Cl bond. So since isa raming ka-electron na itong gigamit to form a bond here, from the homolytic bond cleavage, the chlorine here will get an unpaired electron. So you still get this radical chlorine. And after you get your radical chlorine, you can have the chain termination step. So it must encounter another radical, let's say Cl dot, to form the chain termination step, or another Cl getting a radical to form another termination step. Okay, so that is for the reaction of the substitution reaction for at allylic positions. It's the reaction will be same to that of an alkane. No, if you have alkene, no, with an allylic position, so we just have to be careful on the conditions that we present. Okay, so let's look at another reaction. A bromination reaction. This time we use another reagent. We call this one as N-bromosuccinimide. Okay, so the N-bromosuccinimide is in this structure here. Okay, the propene undergoes allylic bromination. You have another alkene here, and you have N-bromosuccinimide in the presence of light, or a peroxide here. We actually obtain a substitution reaction here. Okay, so again, what you will see here is that the N-succinimide, NBS, or the N-bromosuccinimide, will be our source for bromine. Okay, you have here, and what we will get in the product actually is succinimide. So the bromine here is placed with hydrogen, and the CH, the hydrogen here, is placed with bromine. We have here an allyl bromide. So the propene undergoes allylic bromination when it is treated with N-bromosuccinimide. So any allylic position can actually do bromination in the presence of NBS, or N-bromosuccinimide. So let's look at the mechanism. Let's say you have already produced your Br dot, no, from your N-bromosuccinimide. Once you get your Br dot from NBS, actually form a bond with hydrogen. It will abstract the proton from our hydrogen at an allylic position to produce your HBr. So one electron to form a bond with hydrogen, another electron to form with Br here, another one electron, you actually have your HBr. So from the CH bond, one electron will go here. So you have an arrow, one side arrow here. So your product, you have your CH2 double bond CH, CH2 dot. Okay, you have an allylic radical. So once you get your allylic radical, then it can react with another Br2. Okay, so you'll have again a homolytic bond formation, one electron from this carbon and one electron from this bromine. Okay, you see here there is this homolytic bond cleavage. You actually have, you get one electron from bromine here from this bond, and you will form this one, CH. Okay, copy this, you get your C bromine. And this bromine atom will have an unpaired electron, so we designate as Pr. That is a halogen radical. And this is the chain propagation step. Now, once you have your radical here, you can terminate this again with the encounter of another Pr dot, or another inaning a radical, or any other radical can be terminated. Okay. So, yun sa nato pag form. Here in the reaction, you notice that our source for Br is the N-bromosuccinimide. So let's look at ang reaction sa N-bromosuccinimide. So N-bromosuccinimide is a solid that provides a constant but very low concentration of bromine in the reaction. So what happens actually in the presence of HBr, we actually obtain Br2 here. No, so it will still have to react with HBr. It does this by reacting very rapidly with the HBr formed in the substitution reaction. Here you will You'll see here, right? As you have your Br dot, you actually produce your HBr, and your HBr will react with N-bromosuccinimide, and then you will have your Br2. From the Br2, okay, you have your Br here, it will react with the allylic radical to form your halide. So here it provides a low concentration of your your small amount of your Br dot. Okay. So we just get a small amount of your Br dot, and the main propagation step is by the formation of the NBR band of the NBS. From the NBS, can you get your Br? Okay, so generally, kanila yung tinawag yung reaction, the presence of light and ROR. This one can be broken, the Br dot, and as the reaction proceeds, we actually produce Br2, and the propagation once you get your allylic radical will form your allyl bromide. Okay, so your agents, you have your NBS in the presence of light, or your initiator, the peroxide, to produce your Br dot. Okay, so here is another reaction of an alkene in the presence of NBS and bromosuccinimide, and our initiator, ROR. We have a substitution reaction at the allylic position from that of our carbon double bond. Okay, so under this condition, that is in the nonpolar solvent and a very low concentration of bromine, Br2, very little bromine adds to the double bond, and it reacts by substitution and replaces the allylic hydrogen. Okay, so the mechanism for this is just same as kanina tong diskutan here. So we can start here, no? You can have your Br dot. Again, your Br dot will be the source katong from a very small amount of your Br. Okay, so you have a substitution reaction. In general, the NBS, or the N-bromosuccinimide, is a good reagent to use for allylic bromination. So whenever you encounter NBS and you have an alkene, no, and you have your presence of light, no, it will be the source of bromine for an allylic substitution via radical mechanism. So here, let's examine the bond dissociation energy. The bond dissociation energy of an allylic carbon hydrogen bond, and compare it to the bond dissociation energies of other carbon hydrogen bonds. So here you have your CH at an allylic position, and we do the dissociation energy, DH. We actually have 369, it's positive, no energy is absorbed once we break a bond, and you compare it 1, 2, 3. Compare it with propane. No? Propane with no double bond, no, it's actually much lower than your propane to produce this 1 degree radical. So there is much stabilization to the radical that for the allylic radical than a 1 degree radical that you obtain from propane. Okay, and even much lower, no, for a 2 degree radical gikan sa propane, like this one, or even much